Okay. Keyword operations to make the integer 0. So you're given two integers num1 and num2. In one operation, you can choose integer I in the range of 0 to 60 and subtract 2 to the ith plus num2 from num1. In one operation, you choose integer I, which is in the range of 0 to 60, and subtract 2 to the ith plus num2 from num1. Return the integer denoting the minimum number of operations needed to make num1s equal to 0. If it's impossible, return -1. Huh. What? So you're trying to make num2 to come to 0. Subtract, no, you're trying to make num1 become 0. 2 to the ith plus num2. So you can choose any power of 2 offset by num2. So like 4 minus 2 or 2 minus 2. 4 minus 2 is just 2 though. You can make 3 equal to 0 for the following operations. Choose I equal to 2, 2 squared plus -2 is, that should be 2. And 3 minus that is 1. Choose I equals 2. I see. 1 minus 2 is going to be -1, and then you choose 0. 2 to the 0 minus 2 to the 0 plus -2 is -2. -2 minus -1 minus -2. Wait, what happened here? Choose I equals 0. 2 to the 0 is 1. Oh, 1 minus 2 is -1. -1 minus -1 is 0. Okay. Okay, let me think about this. So I think what you would do is you choose the biggest number that's still smaller than it, closer to 0, I guess, if it's negative. So 3, you wouldn't choose 4, although you could choose 4, no? 3 minus 4. 3 minus 4 would give you -1. No, you couldn't get 4. Yeah, you could get 6. 8 minus 2 is 6. So you could have done 3 minus 6 would give you -3. Yeah, you'd always choose something smaller, I think. So the smallest thing that you can maybe have that's absolute y smaller than that is going to be, or absolute value of the current number smaller than absolute value of the current number is going to be 2. 4 minus 2. That makes 1. Then from 1 you chose to subtract -2. No, 1 you subtract another 2. Interesting. 1 minus 2 is going to give you -1. So that's not, my theory there was incorrect. Okay, so say 5. So you can subtract offset by 7. So if the lowest thing that you can subtract is 7. 7 plus 1 is 8. No. 2 to the 0 plus 7 is actually 8. So the smallest thing you subtract is 8. Or 9. Or 13. No, 11. Oh my god. 11. 4, 8 plus 7 is 15. So you can subtract 8, 9, 11, or 15. So 5 would never reach 0. Okay, so let's do that first example again. So num1 is 3. So if you have, okay, so the powers of 2, 1, 2, 4, 8, 16, 32. Offset by -2 would be -1, 0, 2, 6, 14, 16. Oh, that's okay. 30. So 3, you can't subtract 2, or you could, it's subtracting -1, so subtracting -1 is adding 1. So you still have to subtract 3 by 2 and you get 1. You have to subtract 1 by 2 and get -1. -1 by -1 gets 0. It never makes sense to subtract 0. Subtracting -1 or any negative is incorrect if you're dealing with a positive number. But if you're dealing with a negative number, then you want to do any negatives. So it's you subtract the biggest. Actually, is that always the case? I think you always subtract the biggest number that's still smaller than it on the same with the same sign. Okay, let's try something that is a little more unorthodox. So let's say the offset, the num2, which is the offset, is, let's say, -20. 1, 2, 4, 8, 16, 32. Offset by -20 would be -19, -18, -16, -12, -4, 12. So those are the things you could subtract. Let's go one more, 64. So let's say num1 was, I don't know, num1 is 25. What would I do here? I mean, let's say something very peculiar, where if you actually did the optimal way, it would be subtracting a negative and then doing 44. Like, let's say it was 28. Theory 28, you would, or let's say 40. 40 might be a little easier. 40, you subtract the -4, and you get positive 44, and 44 you subtract there and get 0. Or 40, subtract 44, 44 you get -4, -4 you get 0. If you try subtracting 12, 40 minus 12 is 28. And then 28 doesn't work. I wonder. Is this the same? So each time you do a subtraction, that's another offset. Each time you do a subtraction, that's another offset that is being subtracted from the total. So if you have a starting number, is it somehow related to the first time you see a power of 2 within the sequence of numbers where each number is increased or decreased by the offset, the num2? then you can also choose to change it by power of 2 step as well. This 0 is the offset is 2, the power of 2 is 2, so it's yeah. If we had 40 to start with, so 40 is closest to 44, but if it was something like it was something like yeah, it's close, like let's say 28. 28, you should still want to subtract. When you do subtract 44, you get negative 18. But if you subtract a 12, you get positive 16. Positive 16, then you have to subtract another 12. Huh. Return the integer denoting the minimum number of operations. I is 0 to the 60th power, that's really big. Num1 is 10 to the 9th, possibly. Up to 10 to the 9th. Subtract 2 to the ith plus num2. Okay. In one operation. I wonder if it's like, okay, so there's 60 possible values, 61 possible values that you can subtract the original num1 by. 61 possible values. And then each of those has 61 possible values that you subtract the next number by. Oh. $61 possible. And we're denoting the minimum number of possible operations. Yeah, it's a little big branching factor to track every single possibility. I think could use a heap, where the heap is what? The heap is how far the current number is from from 0. The heap has the size of, I don't think that works. How far the current number is from any power of 2. If I kept track of a heap, so if I started with 28, and then I subtracted all the possible powers of 2, restored it into the heap, put it back into the heap. How would I know when the heap doesn't work anymore? So 28, I subtracted, I would do minus negative 19, minus negative 18, minus negative 16, minus negative 12, minus negative 4, minus 12, minus 44. Minus 12 would give you 16. Minus 44 would give you negative 16. So they're equally as far away from 0. If evaluates positive 16, then it would do another minus 12 and give you 4. And that would still be the closest away from 0. So it wouldn't necessarily even evaluate the negative 16 correctly. If you didn't choose a heap, let's say you chose term integer denoting the minimum number of operations. Okay, let's think about this. Say you have a start, let's say the start is k. So eventually have something where it's 0 is equal to k plus, let's say your answer is let's say p operations. P times num2 plus sum of some powers of 2. Sum like 2 to the first plus 2 to the third plus 2 to something. K plus P times num2 plus some sum of some number, some powers of 2. So k plus p times num2 is equal to negative of some sum of powers of 2. K plus p times num2. And if you deal with sum of numbers, sum of powers of 2, is there any particular property of them? So in theory, 1 would be part of that sum. So 1 is always doable. We have a bunch of 1s. This should always be doable, assuming that this side is starting in the negatives. Okay, so let's look at example 1. K is 3. 3 plus P times -2 is negative of sum of powers of 2. So P has to be at least 2 here. 2 times -2 is -4. Here P, no actually P, and P equals the number of, is equal to the count of values in the sum. So it can't just be 2 here. 2 times -2 is -4. -4 plus 3 is -6. Or -4 plus 3 is -1. But you need to have 3 values here. Or you need to have 2 values whose sum is -1, which doesn't work. So if P is 3, that means 3 plus 3 times -2 is 6 plus -6. 3 plus -6 is -3, which is equal to negative of 1 plus 1 plus 1. Each power of 2 that you add, that's another offset that we're dealing with. The answer was in fact 3. Was there another way of getting there here? -2. -2 is the offset. So if I chose I equals 1, that gives you 0. If I choose I equals 0, 0, 2 to the 0, 2 to the 0 is, I think that's just the opposite sign. 0, it's K minus this. K minus this. Okay. So if I move this thing to the other side, then it's sum of powers of 2 . So this thing should be minus. Okay. Interesting. How did this work out? So P ended up being 3. 3 times -2 should be -6. Minus -6 ends up being +9. And the sum of powers of 2 to get 9 would be 3 numbers whose sum add up to 9 would be 1 plus 8 plus 0. No, 0 is not power of 2. 1 plus 4 plus 4. Three. Yes. Okay. Let's do example 2. 5 minus P times 7 is equal to sum of P terms that are powers of 2. So if p is 1, then you already have a negative number here. If p is 2, then you already have something that's impossible. Okay, so p is 1, you already have something that's possible. Alright, what was the other one that I was working on this thing? Let's say the number was originally 28 and num2 was negative p times negative 20. So p powers of 2. So this ends up being p is 1, then it'd be 48. P is 2 ends up being 68, or 68 could be 64 plus 4. 64 plus 4. Or it could be 32 plus 32. No, 68. No, it's not. 64 plus 4. Huh. So p is 1. This is saying ends up being 48. P is 2 ends up being 68. And 28 plus 40. 68, which is 64 plus 4. So p, so you works with two terms or two operations. Each operation is another offset, subtraction, and another power of 2. Subtraction, really. How to logically think about that. So this is just a linear type deal. Your slope is your num2. P is like x, that's mx plus b. Num1 is your offset. But I don't know what this means. Sum of p power of 2. Like, what is that? What is the space of those possibilities that are the values that you can get by any combination of powers of any combinations of x or p values that are powers of 2. Like you could be adding 128 with 2. We can add 64 with 16. Is there something that makes sense? So the powers of 2 could be 2 to the 0, 2 is 1. So it should almost always work. guess this is an increasing number. This is could be a strictly decreasing number, so could not intersect. 5, especially if it's initially going to be negative. If it's initially negative, then there's just no way. So I know that if I make a certain number of moves, certain number of operations, I know. Actually, does it have to be at least one operation? I guess num1 isn't initially equal to 0, so it can't be 1. It can't be 0 operations. Okay. So I know after p number operations what the value of the sum of the powers need to be. Strictly the sum of the powers, not including the offset. So when p is 1, I know exactly what the sum should be. When p is 2, I know what the sum should be. So that's fixed. So the question is, I know what the sum should be. How do I choose the least? How do I choose the least operation? Could possibly do a binary search, because if it can do it in p operations, then it should actually binary search. If you can do it in p operations, then not quite. And there's no guarantee that I can do it in p plus 1 operation, I don't think. Yeah, there's no guarantee there. It's probably not binary search. So target number. So for each p value, where p is the number of operations, I go through every possible sum of values that number of powers of 2. Oh, I see it. I see it. This is. I think I. So, if I think in binary, if powers of 2 in binary have, or say different powers of 2, have a single bit that is 1, other bits are 0. So for example, let's say 64 is in binary 1 64 032 016 08 04 02 01, so something like that. And if you have a number that is, let's say you have a number that is 13. 13 is going to be in binary 18140211. So 1 plus 8 plus 4 plus 1. Right? The number of powers of 2 that would be needed to get to 13 would be at minimum 3. At minimum 3. You could do it with more. For instance, you could break down the 8 into 4 and 4. But this basically needs at minimum 3 powers of 2 in sum. But could be more. So if I look at the values that the sum would have to add up to, which is the kind of linear mx plus b, where basically num1 is b and num2 is m, x being the number of powers of 2 in that sequence. And I look at the number of bits that are on, the number of ones within that binary version, and it matches the term in the sequence, then that would be the least. Does it need to match, or could it be less or more? So if it's 3 terms in and the number of bits is 1, if it's 2 terms in and the number of bits is 1, then in theory I could do a lower power of 2 plus a lower power of 2, like 2 bits in, the sum is 64, I could add 32 and 32. But if it's like 3 bits in, the sum is 64, then I can't add 32 plus 32 plus 32. Huh. So close, I think. So I look at the number of bits that are on for each term in the sequence. And the first term in the sequence, where the number of bits that are 1, that matches whatever term the sequence it is, or that so let's say the sequence is 4 plus 30 plus 30, or let's say 4 plus 20 plus 20 plus 20. So that adds up to 64. So that means that 3 terms 3 term sum of powers of 2 that adds to that. Two terms is fine. Two terms is fine. 64. Well, it should be 32 plus 16 plus 16. But then if it was something lower, let's say it ended up being, I think this thing needs to have at least be that power of 2. So what's the smallest? So like it can't be something like -1 or +1, right? Like if the 3 terms added 2, let's say, let's keep it simple. Say -5 plus 2 plus 2 plus 2. That's the 1. And I would need to have 3 terms. Let's sum 3-term sum of powers of 2. That's to 1. That just can't work. Like there's just no, 1 is too small. But if it's anything that is the lowest it could be here is 3, right? 3, which is 1 plus 1 plus 1. Lowest is 3. It could be 4. 4 would be 2 plus 1 plus 1. 5. 5 would be 5 would be 2 plus 2 plus 1. 6, 2, 2, 2, 7, 4, 2, 1, 8, 4, 2, 2. Okay. Seven, 4, 2, 2. It just can't be something that has more than it can have. It needs to be something where it's at least p in value. So p is the number of terms, it has to be at least that. So it can be at least 1 plus 1 plus 1 plus how many p's. And it needs to have bits. The number of bits that are on can't be more than p. So it can have at most p bits that are on. Okay. The question is how to quickly find the number of bits that are 1 in a binary number quickly. Python, fastest way to count number of 1 bits. Is it bit count introduced in 3.1 number.bit count? Wonder how fast that is. Okay, but I think so. K is num1. No, K is num1. Yeah. So I think K is num1. So let's say the value is originally num1 plus num2. Each time no, this is minus num2. So answer is equal to 0. Or let's say answer is equal to 1, maybe? What am I assuming it's going to be? I'm assuming answer is originally 1 operation. Okay, so and then each loop I need to, so this number has to be positive, I think. If this number isn't positive, then there's just no way this, well, that's not true. If I subtract, if this number is, okay, num2 is how much I'm decreasing by, p times num2. So if this is a negative number, that is, if this number is negative, value is less than or equal to 0, and I'm decreasing by num2, and num2 is positive. Num2 could be 0, huh? Yeah, I think this is right. So if I have a neg number and it's decreasing, then there's no way that the sum of those numbers is ever going to reach positives. I guess I could also say this is 1 value, no, I think it's 0. If it's 1, then in theory it should work. And then if the value is greater than or equal to 0, if it's already positive, no, then that's still fine. Value is negative. Well, maybe I should just not do this way. Alright, let's try the non-trivial or non-edge case of impossible. So the value num1 minus num2. So I can say while value is I'm not sure what the actual condition of the while loop here is. So while value, let's say 1 bits are going to be the value dot value dot bit count. And if the value is greater than the current answer and the 1 bits is less than or equal to that answer, then return the answer. So if there's 1 bit that's on and the answer is 1, if the value is at least 1, value is greater than or equal to the answer. So value is at least 1, and there's only 1 bit that's on, then there should be 1 power of 2 that works. Otherwise, do the loop again, the value, I think let's just do while true here. Next time I do the loop, it should be the value minus equals another num2. So next time I do the loop, value changes, count the number of 1 bits in that. The answer is now 2, if the value is at least 2, and the number of 1 bits here is at least is less than or equal to 2. Okay, there needs to be some sort of stop here, and I return like -1 here. So what's the condition? What is the condition? So this condition should check when it's impossible. It's impossible. Where was it? 5 minus p times 7. This was impossible because this value was positive, so you're decreasing. How do you detect when it's impossible? The current value is negative. If the current value is negative and let's see here what's true. I guess I can do here if value if while value could be negative, that's fine. If the value is negative here, less than or equal to 0, and num2 is greater than or equal to 0. The value is less than or equal to 0, and num2 is greater than or equal to 0. So it's a decreasing summation. Otherwise, if the summation is positive, or num2 is, so I think I mean De Morgan's law for this, I think it's De Morgan's law, to reverse the negation of this. If this is breaking, then this should be true. It should be true during the loop. So the reverse of this logic would be value greater than 0 or num2 less than 0. Right? Num2 greater than or equal to 0, negation dot num2 less than 0. So while the value is positive, or num2 less than 0, why does that work? So the negation of this is when you continue the loop. So if not this, negation, so you distribute the negative, so negation of value less than or equal to 0 is value greater than 0. Negate the and, or negate the num2. I mean, this works logically, I'm almost certain, but this is based on logic rather than full reasoning power. Like my reasoning power currently is not capable of defining why it works. While the summation is greater than 0, or is this an OR here? Or why is this condition continuing the loop? Wow. Or you are continuing to I see. It's num2 is negative means that later on terms in the sequence is increasing. So yeah. Loop. Not possible. Keep trying to find some possible sum of powers as long as the sum is positive, which possible is negative. Can't have a summation be negative. Actually, the value here is like the sum of powers. Or if num2 is negative, which causes sum to increase with additional terms, with additional operations. Okay. Okay. I think so. That is it. Wow, that was yeah, that's kind of tricky. I had to really think about that. Okay, so for the summary here, it's basically so consider that the number of operations is treated is variable p, then the equation that relates to the sum to the relates to this can be thought of as 0 equals num1 plus p times or minus p times num2 minus sum of p powers, p terms, powers of 2, which therefore has num1 minus p times num2 equals sum of p powers, p terms of powers of 2. Then consider that powers of 2 then consider the binary version of num1 plus num1 minus p times num2 has some number of bits that are ones. Those can correspond to the power of 2, the correspond to the minimum number of powers of 2 necessary to get that number. So for example, 13, which is in binary 1101, needs at least 3 powers of 2 to get it. So thus use track the sum of the value of num1 minus p times num2, which is sum of powers and above. Identify how many bits are ones in that sum using integer dot bit count for Python, and see if that is doable for that number of operations. So for example, if value has 3 bits, it can be doable in anything that is 3 or more operations. So count the bits. If it needs to also be at least that value. So if the sum of powers is 5, then at minimum it's going to be 5 operations. It can't be like, you can't add, at minimum it has to be like 1 plus 1 plus 1 plus 1 plus 1 5 times. And if the sum of powers if the number 1's bit is like 10, then the answer needs to be at least 10. Can't be less. Alright, anyways, time complexity also has some logic for when it's not possible for any sum to get there. So break loop, break attempting when value is negative, when sum is negative and num2 is negative, or num2 is positive, since num2 decreases the sum each turn, each operation. Time complexity is going to be 01. 01? Really? Yeah, it's pretty much a 1 since this will have some finite number of bits to work through. Yeah. There's going to be at most like 30 something bits maybe. Each iteration of the loop basically increases the number of possible bits to compare to in the space of bits, in the space of numbers. So 32 loops equals 32-bit space. So it's very finite. 01 for space complexity, as no additional space is needed. Whew.